diminuer, on s'en fout.
Ok. Là,
Voilà.
on s'en fout, on le laisse à côté. Et là, on vérifie ici.
Là, on va le voir. Ouais, si tu veux, moi, je vais vérifier plutôt sur mon téléphone. Donc ça, c'est un
Double check.
non, mais c'est mieux parce que ça fait.
Ah.
Donc maintenant, bah, ça, tu laisses, tu reviens.
Ouais.
Et tu coupes le son par contre de nickel parce que sinon ça va ressortir.
Ouais.
Voilà, tu coupes ça.
Moi, je peux même.
Voilà. Et là, tu reviens dans une.
Non. Bon.
Et tu fais juste arrêter la vidéo. Voilà, comme ça.
Hello. Hello.
Hello, Gustavo.
Hi. Hi, Yuan. How you doing?
Alors, on a coupé tu te rappelles, on a coupé la vidéo et le son.
Donc, yes. Can you see us? Can you see me? Everyone. Okay, let's go.
Very nice. Yeah.
Okay, I think it's technically. So we will wait for the other members of the meet because they are launching, I think. Okay.
I'm gonna grab a coffee and I will be back in 1 minute, okay?
Okay, okay, no problem. Moi, je vais couper le son. Je vais couper le son. Je ne sais pas comment couper le son facilement. Hi, Rose.
Hello. Yep.
It's kind of. Can you hear me? Well, I can hear you.
You cannot hear me?
The first phrase, but the second sentence, yes. This one, yes.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay, I can hear you now. Great. Okay, no problem with the sound, with the video. And can you see share the screen?
Yes.
Okay, nice. Nice. We'll wait for the other member of the jury.
Just a question. Can I share the Zoom link to some people from my team because they were interested in attending? Is it okay?
Of course, yes.
Thanks.
Just a YouTube link, not the Zoom link. Just
Okay. Where I can find this YouTube link then? Is it in one of your...
Okay, I'll try to send you by email right now.
Okay, if it's a problem, don't worry about it. It's okay.
Okay, so I'll send you this. Wow. Normally, I send you the link by mail.
Okay, thank
Donc après, je vais l'entrer dans les discours. Donc je fais 8 minutes de discours, la qualité est pour un temps, et le reste, c'est l'entrée. Moi, je les ai repris. Enfin, les rapports de voilà, les rapports de la. Ah oui, c'est ça. Oui, tout à fait, oui, absolument. Ah oui, d'accord.
Oui, les arbres, on te voit, je pense. Si tu parles, la caméra.
OK. C'est bon, on me voit là? On ne me voit pas. OK. Gusto, Alexandros, you hear us?
Yes, loud and clear.
Okay, fine. So thanks a lot. Thanks a lot for your participation. So we will start. Okay. And so it's 45 minutes by Yuan. Then we have a series of interactions, questions. Okay. And then we have a small discussion inside the jury, and okay, and that's it. Okay. So we'll start.
Okay, so welcome to everybody to the PhD defense of YIN. I'm Paola Cinella. I'm a professor here at Sorbonne in the Department of Mechanics, and I am the chair, let's say, of this committee. So, Don-Din, you have, as Patrick said, 45 minutes, and then I will start with questions from the two reviewers. So first Christian and then Alexandros, and then we go on with the other external members of the committee. So,
Thank you, Paula. So, good afternoon, everyone. Thank you for being here today. I'm sorry. Oh, thank you for being here today. So, in the next 45 minutes, I'll be very glad to. Désolé. How will we start? So, in the next 45 minutes, I'll be sharing with you this very exciting journey of my PhD on physics-aware deep learning and the dynamical systems focused on hybrid modeling and with this generalization problems. So, in this presentation, I will first provide you some context to this thesis to set the stage, and then I'll discuss our four main contributions one by one, and I'll conclude the presentation by some future perspectives. So let's begin with the context. In nature, we observe a lot of physical phenomena, and all these phenomena, sometimes they change over time. For example, in a very large scale, when we look at the universe, we have planets moving. When we see the clouds are driven by wind. In a smaller scale, we have how water runs. We see how the parts are moving. Okay, I'll restart. So with the interruption. Okay. So here in a smaller scale, we see how water runs, how hearts are beating, and we see also how chemical components are reacting. So this phenomenon evolves over time, and they offer a lot of insights, very deep insights inside the governing law that is running our world. So we are urged to understand what's going on behind all this phenomenon. It is often driven by some very practical needs. For example, we want to do some spatial temporal predictions. We want to know how the planet moves, what's the weather of the next day, next month, and what's the climate of the next decade. And also, we want to do some prototype and design for some daily vehicle, such as a bullet train or an airplane. So in science, we model all these phenomena typically by describing how the current state of the phenomenon changes. And this led us to some very useful tools, which is called differential equations. And all these tools and concepts help us to make models. But what kind of model we make? And as Yuan said, in science, we make models that describe a large number of dynamics. And all these models should reflect what's going on in the real world. And how do we do in physics? First, we observe this system, and then we collect the data. We try to understand what's going on behind this data. We analyze them, And then we make model. We use this model to predict the data. If the prediction does not correspond to the data, we'll adjust our model until it reflects the reality. So these models contains a very principled understanding of all these phenomena. However, when we try to make use of these physical models, they are not easy to be used in practice. For example, when we try to produce some very precise solution to a certain phenomenon, it is very costly to solve, and often the phenomenon itself is not fully understood, so we cannot make long-term predictions. And so in recent years, there's been a very popular trend to use data plus machine learning approaches as an alternative to these physical models. And deep learning success in many other domains have motivated us to transfer all these deep learning techniques to dynamics model. However, when we try to apply
We lost them,
Something happens, right?
but not to us.
No. Or maybe, I don't know, some strange event happened. Okay, I don't know. Should we send an email or something? Well, probably the notices, right? But still, we are live. No?
Yeah. Oh. We see the.
Alexandros, did you send an email or something? Or
Yeah. I said I just sent an email to Patrick.
Okay.
Maybe it might be useful to send him also a message.
online.
Ah, c'est bon, c'est bon, c'est bon.
You hear me?
Yes, welcome back.
Yes, sorry. We lost you until when?
Slide
Which
2.
slide?
Data and ML. Data and ML slide.
Yeah. Very sorry for this connection issue. I don't know why it happened. From this side of the slide. Yes, at the end of this slide.
Yes, but we don't. I don't see the slide now. Huh? You don't share.
Sorry. I have to share the screen. This is this happens. Public seems to be done as well. YouTube link seems to be done. YouTube link. I think YouTube. YouTube link.
This is where we lost you.
Yes, that's the one.
And YouTube link is down. I think normally it's go back on YouTube. You can check it. Normally it's the same address. Okay, the score is also good. Anybody check the YouTube? It's on. Okay, working. Okay. For the technical issue. So I will go back to the presentation. I'm just to move these small windows. Oh, I don't know. To read here. It's okay. Okay. So I will take the presentation. In recent years, we have a very popular trend of using data plus machine learning approaches as an alternative to physical models. And in recent years, deployment success have motivated us to use them for a dynamics modeling. However, when we try to apply all these techniques blindly, we won't have a good result because they have many limitations and they are not often enough for dynamics modeling. So in this thesis, our goal is to break all these limitations, some of these limitations. So it's very ambitious. Okay, so we address them through several research questions. In the first place, we need that our model to produce very physical and meaningful results. And in this case, it is very natural to consider the existing physical knowledge. And our question here is, how can we make use of it? And the next questions are about the generality of these models. When we look at different systems, first, we want to understand what are the commonality between these systems. So we want a model that discovers all these commonalities, and also by understanding the differences between these systems, we want a model that can be adapted easily to a new unseen dynamics. So here we ask ourselves, how can we do this with deep learning? And the fourth question is about the form of the data. So in real world practice, in real world scenario, we rarely have equally distributed data in space and time. So we want some model that can handle this kind of data, and we discovered this continuous dynamics modeling for this purpose. So in the following, I'll present these main contributions one by one to answer each of these questions. Affinity for the hybrid modeling, leads and CODA for the generalization problems, and also Dyno for continuous modeling. So let's begin with affinity about hybrid modeling. So to begin, I would like to motivate further this idea of hybrid modeling. So what is hybrid modeling? It is using, it is combining the physical model and the machine learning model. As we know, both of them have a lot of positive points and negative points. For example, we have physical model here. They have very strong physical information inside, and they are sometimes very interpretable. On the other side, we have very powerful machine learning models that are designed to fit data, and there are many very flexible algorithms exist. So what we ask ourselves here is, how can we leverage the strength of both of them? In our community, we have already proposed a lot of approaches that try to do this hybrid modeling. So they have different degrees of interactions and importance of both two parts, from just replacing some components inside a numerical model to regularizing the results of neural networks with physical constraints. So in this first work, affinity, we position ourselves in a place where both components play equally important and the indispensable role in modeling the dynamics. So it is a side-by-side cooperation. So let me introduce the setting of the problem that we're trying to solve. Here, we try to learn a unknown dynamics that is described by an unknown function f, and this function should belong to a function space. And in the system, as you can see, we have ut that describe the current state of the system. If this ut is a vector, it will be an ODE, ordinary differential equation. And if ut is a function, it will be a partial differential equation. And we assume that we observe this function f through a set of trajectories. And also we assume that we have this incomplete physics model that contains a set of very feasible functions. So the objective here is to augment this incomplete physics model with a machine learning model. And then these two models together will predict correctly the entire dynamics. So let's take a simple example to show this idea. First, what we want to do here is to predict a density function. If we use purely data-driven models, in some situations it will predict very non-physical prediction because you have no physics inside, you have no physical information. And if you use an incomplete physical model, for example, here we took an ideal pendulum without the damping term, it won't predict well and it won't predict the correct parameter. So our goal here is to use a machine learning model to learn the damping term, and then these two terms together will predict well the entire dynamics. So the idea here is to decompose this target dynamics that we've seen before. And it is decomposed by an addition of this physical component FP and this machine learning part FP. It's worth noting that this assumption of additivity is not very restrictive because every function is a vector and every vector can be decomposed in this way. And also in physics, we have the same intrusion. For example, when we add some forcing terms, we try to add an additive term after the entire model. However, when we try to apply this decomposition, it has an infinity number of decompositions exist. So any direct application of this decomposition to formulate optimization problem will be ill-posed. And our goal here with affinity is then to make this decomposition well-posed. What's the intrusion here? The intrusion here is we want to maximize the influence of this incomplete physics model. So, it is equivalent to just to say that we will complement this physics model with a machine learning model only when we need it. So we then formulate this idea into this optimization problem. There are two constraints inside this optimization problem. First, you have this constraints on the derivative of data, which means that the sum of FP and FA should predict the correct rate of change observed in data. So this constraint will ensure the accurate prediction on the training data. And the second constraint is that we should minimize also the contribution of this machine learning model. In theory, by solving this affinity optimization problem, it will give us a unique decomposition of the target dynamics into a unique FP and FA. So in this way, we can guarantee the parameter identification inside this incomplete physics model. And also, it will guarantee the accurate prediction within this entire model. And in practice, we try to implement this physical model with parameterized equation. And also this machine learning term with neural network, both models can be optimized through updating their corresponding parameters. And in the original formulation, we need to predict the derivatives. We need to predict derivatives of this entire system that corresponds to the data. However, if we try to apply directly these constraints, we have to estimate this derivative, and it will add some estimation error when we try to unroll this learned dynamics. So to solve this problem, we try to take the integral form of this constraint. So on the left-hand side, if you integrate this term, you will find the trajectory data that we have seen before. And if you integrate this term, we will find the prediction, the predicted trajectory, the unrolled dynamics from the initial condition u0. So this allows us to reformulate this constraints to a classical squared loss between the trajectory that we observe and the predicted trajectory. So it is worth noting that this result is integrated by a numerical solver. And then this solver should be differentiable because we want to update the parameter inside FB and FF. And also this implementation is used in all the substantial approaches that we will introduce later when we try to learn dynamics inside. Well, so when we try to solve the entire affinity, we use its Lagrangian formulation. So on the left side, you can find the minimization of the contribution of the machine learning part, and on the left side, you can find the prediction part. And how this works, it's literally saying that if your FA is too small and it hurts the prediction part, and this lambda will go up to emphasize the loss of prediction. So this thing will allow us to strike a balance between the minimization of the contribution of the part and also the prediction position. So here we demonstrate the effectiveness of our affinity network with a sample system. So here, as you can see, it is a reaction diffusion PDE. We have the true system here. It's the entire system, and that we can see. So on the right, on the left, you have the diffusion terms, and on the right, red terms, you have the reaction terms. And we consider an incomplete physical model that contains only the diffusion parts. So as you can see, here, this is the unrolled dynamics of our affinity, and this is the reference data we test. As you can see, when we try to predict until the horizon, it predicts still correctly, and also we predict well the corresponding parameters inside this incomplete physical model. So quantitatively, in terms of prediction, we reduced over 99% of the prediction error with respect to our incomplete physical model, and also about 70% of the error with the state-of-the-art with respect to the state-of-the-art machine learning model. It is worth noting that we have still some distance between our model and the true PDE. However, this true PDE is not reachable, and is just a gold standard. And in terms of the estimation of parameter, we also reduced over 90% of the error. So in the next two sections, I will talk about the generalization problem for deep learning dynamics model. I will introduce two models that work with data from different environments. And the first one is LEADS. It focuses on learning commonalities from different systems. So this work has been motivated from some very real-world scenario. Imagine that we try to learn some dynamics in the ocean, and when we have retrieved some data from these yellow circles, this different region from the circles, and the data retrieved will be associated to this environment, and they will influence by the distinguished characteristics inside this environment. And also these characteristics may influence the underlying dynamics. And also in some situations, we have very limited data in each of the cycles. So as you can see, if we try to apply the existing classical approach, for example, empirical risk minimization, we'll just mix all this data up, and the result is just a mean model that that underperform in any of these environments. So instead, the model should be aware of the existence of this environment, and that's what we propose to do. So now we can describe our setting. We want to model a set of we want to model a set of different systems. So we suppose that we have access to a set of environments, and in each of these environments, it has its independent governing dynamics. We assume always that we observe all these dynamics through a set of trajectory, and in addition, we know that from which environment these trajectories are calculated. So we want that our model first to capture all the shared characteristics across all the environments, and then it should keep its predictability in each of these environments. So the idea here is then to decompose these dynamics, each of these dynamics, into two terms. For each of these dynamics, we have on the right-hand side, we have a common dynamics F, which is shared among all the environments, and also environment-specific GP that provides a little correction. So the intuition here is then to let the shared term F to absorb all the common information as much as possible, and then we let this environment-specific term to just do some little corrections. So, so to achieve this, we minimize here this contribution of all these environment-specific terms R of GE, and this function R here, we will measure the size of this GE, and we will talk about later about the choice of this type. And we have also this constraint on data, so we have to you can show the accurate prediction in every environment through this constraint. So solving this problem will give us some theoretical results. First, at the end of the training, we have a unique decomposition of all these dynamics. So this will lead us to a well-defined solution at the end, and the solution is stable. And then the second aspect concerns the generalization problem. So in theory, as we know, in order to reduce this test error, we should limit the model's capacity. So we know already that when we learn a shared term across as many environments as possible, it will reduce this capacity. And also, in addition, if we try to improve further this generalization power, we should limit the GE's capacity as well. So this motivates us to choose these are that will constrain capacity of our G. So we have we have found some quantities that describe the capacity of this GE, such as, for example, if you have a neural network, we can choose its L2 norm, of course, approximated, and also some spectral norm of this neural network. So we now show the effectiveness of this framework. In the first row, you have 4 different environments of a local preparator system. And they describe the interaction between a pair of prey and predator. On the x-axis, you have the density of the prey, and on the y-axis, you have the density of the predator. And each environment, inside each environment, they start interacting with each other from exactly the same point, but they have distinguished behavior in each of these environments. As you can see, the purple line here is the ground truth data, ground truth trajectory, and the leads is the prediction of the model, and all these 2 dashed lines are the prediction of the baseline. On the second row, you can find 2 types of different very beautiful PE systems. For the first, we have 3 distinct environments here. On the left, you have Gray-Scott reaction diffusion systems, and on the right, we have Navier-Stokes systems. And we show these 2 results from our baselines, and this result is from our model. And these are these are errors committed by each of these models. So as you can see, these demonstrate better generalization in all these environments. It predicts pretty well, pretty close to the data, and it commits less error in each of these environments. And quantitatively, when we see that the training loss are similar here across the baselines, we reduced over 40% of error during test. And even better, in this very difficult Navier-Stokes equation, we reduced over 80%, around 80% better. Okay, so after leads, we thought about how to push this generalization idea further. This led to CODA. It is context-aware dynamics model. So in the previous approach leads, we aimed at learning commonalities from a set of known dynamics. And then here in CODA, we try to push this idea further to new environments. And we want a model that could be generalized beyond these training environments. To make it work in new environment, we have to adapt this dynamics model. And there already exist a lot of adaptation approaches in deep learning. For example, we have transfer learning, we have meta learning, we have multitask learning, and some context-based methods with autoencoder. However, all these methods may lack of effectiveness or efficiency or accuracy when we try to apply them to the dynamics prediction. So these limitations led us to propose our model. This time, we placed ourselves in an even larger setting, which means that we try to model a family of dynamics. And each of this function at E here will be linked to a context, which could be a physical parameter. And we assume also that we have a very limited number of in-domain training environments, which allows us maybe to learn how to adapt. And then all the other environments will use it as test, and inside you have very limited data for the adaptation. So the objective here is then to learn first a shared model, shared network, TE, and then we use all these in-domain training environments to learn how to adapt. And then we evaluate the performance of the adaptation in any other environment. In this model, the intrusion here is broken into two parts. First, we want the adaptation to be fast. We want a fast adaptation so that we can reach the solution for new environment as soon as possible. And we want also the adaptation to be easy because we need only modify a very few parameters to reach the solution. So these two intrusions give rise to further intrusions for parameterized model. For example, like neural networks. So to go fast, we need to adapt locally so that all the solution will be constrained inside a very local regime. And also, to go easy, we want to adapt our neural network in a very constrained space. Here, the intrusion here is to use low-rank adaptation. So first, to achieve this local adaptation, we try to learn a common data GC that is not far from the solution to all the other environments. So it's worth noting that why this kind of local adaptation is working in your network is still open problem. However, it works in practice, so we can say that we can use it. And so the optimization from here will put some constraints on the different increments to reach the solution to each of these environments, and so that you can see all the solutions to the environment that we have will constrained in a very local region environment. And also we have a surprise here is that if we constrain this implement in a very local region, we will modify our adaptation problem to a very convex around this data set. And to go to do the adaptation in a low-rank space, how can we do that? First, when we face a new environment here, we try to search for we try to search the dynamics function here, G data. We have already learned the common data C. So what we want to generate is this delta data. Instead of just searching in the same space as this delta C, we'll generate it from a constraint space here from practical side E. And then this is this increment is generated through a hypernetwork, a linear hypernetwork. So when you do the adaptation here with a new environment, you initialize this code at 0, you generate this increment, you combine this increment to the common parameter, and then you can formulate this the next model, and you can use it to predict the system. And then if you have some data, you can backpropagate the loss to adjust this code, and then your system is adapted until the convergence of this code. So as you can see, this adaptation is very easy because all these parameters are pre-learned. What you can do is just to adapt this very low dimension code. And also empirically, we show that they are very simple efficient. You can use only one trajectory to fit to a new system. And here, let's see how these two principles works in practice to help this adaptation. Here you have three different environments of the local system, and each of them is the loss landscape projected into the two-dimensional space of adaptation directions. As you can see here, data C is the common parameter, and the yellow arrow here points to the optimum of each of these environments. You can already see the effect of low-rank adaptation because all these optima are included in this 2D plane. And also, you can see all these solutions, all these optima are not very far from this DSC, and the loss landscape is pretty smooth and it's highly convex. And here we visualized the adaptation performance of our problem. On the left-hand side, we have a figure on which each point is a different system. And so we use only 9 of these environments to train our folder model. And then we perform the adaptation to every other environment. As you can see here that the adaptation inside this context scope is pretty well, and outside it works also. So it works pretty magically when you move around this code in this 2D context space. You see that our model will change with the environment, and it predicts pretty well. It predicts pretty well in all the new systems. Like that. So we have compared our model to some state-of-the-art methods in meta-learning, in multitask learning, and some contextual model. And the first, we can already see that with respect to our strongest baseline in all known environments, we can improve from 40% to 60% of error. And then, even better, we are the state-of-the-art in terms of adaptation performance. We gain 20% to 80% in terms of the adaptation error. So, after exploring these multi-system generalization problems, we now go back to modeling single dynamics. And this time, we aim at breaking some limitations inside the existing approaches. So when we try to predict some spatial transfer dynamics, we essentially trying to transform one function to another. And in deep learning, we have many approaches that has been proposed, but all of them struggle with being flexible. For example, we have some classical approaches. We try to use convolutional networks that is very similar to finite difference scheme, and also some graph neural network is similar to finite element scheme. And however, all these architectures are heavily discretized in space and time, and we have some very heavy bias inside these models. And recently, we have some efforts to propose to propose some mesh-free methods, which means that we don't rely on any specific discretization. However, in all this model, we have some constraints on its input and output formula, and sometimes the input and output grid is linked. So to address all these issues, we have developed our Dynamo model to surpass the limitation of the existing operator learning model. So our model Dynamo will benefit from different flexibility capability. In space, it can handle freeform input and on different domains, such as it can handle some data on a plane and on a sphere. And also, it can be easily generalized to new grid. And also, the prediction can be accurate at any position in space. In time, our model will yield time continuous solutions, and it will work with new initial conditions. And it can also extrapolate beyond the horizon that we seen during training. So to achieve all these objectives, we proposed a neural forecaster that is continuous in space and time. To make it time continuous, we use a neural ODE, and to make it space continuous, we will apply a type of space continuous model that I will introduce later. So our Dynamo have 3 main components. the first component here is an encoder. It uses a space continuous model to encode some already discretized signal into a code alpha. And then our dynamics model will learn the dynamics inside the space of this code. And the third part of our model is a decoder, which take this code alpha here, and it will recover the current state with this code. So at the inference time, what we do here is, if we take a new initial condition, we'll encode this initial condition into a code alpha, and then we use this alpha as initial condition of dynamics. We'll predict until some certain alpha t, and then we'll recover the state at time t using alpha t. So what kind of spatial continuous model we're going to try to use? As you can see, we have recently a very nice lineup of works that try to represent a signal with a neural network, which is called implicit neural representations. It takes the coordinates as input and the outputs the values at this position. They are originally proposed for representing some 3D objects like this. It turns out that they are very nice representation for a continuous signal. So, and it's even better. We can learn this continuous representation using by fitting the discretized signal. So we can pass from the discretized signal to a continuous function. So how can we use it for our encoding? If you remember, in Coda we have faced already a similar problem. We used a context-based, context-aware neural network to adapt a neural network to adapt a neural dynamics model to an. So here it is the same situation, because we try to change the parameter inside the neural network, and here we use the same intuition. As you can see, we use this code alpha to represent neural network that will influence the parameter inside this network, and we will use a hypermed that generates directly the parameter of this network to represent a lot of frames, and this code will be able to be adapted through reading designs, just like in code. And how can we learn this dynamics? So just as always, we first use all the available data, U0, we include all of them into a code space, alpha 0, alpha t, and then, as always, we will learn the dynamics directly inside this code space. Here we show the effectiveness of our Dyno framework. Especially this case is when the observation grid is really sparse. Here we show that we use only 5% of the data on the test grid. You can see here, this is the prediction of our Dyno architecture, and this is our strongest baseline, which is based on a graph neural network. And we predict within the horizon, the training horizon, and beyond the training horizon. And also you can see here, these are errors committed by each of these methods. So first, as you can see, already Dyno will produce very smooth frame here, instead of some frames with interpolation error. As you can see that there's a lot in interpolation error inside this graph-based neural network. And also, you can see that our model extrapolates beyond time, and it works pretty well. And quantitatively, we show also that on this very sparse grid, we reduce over 80% of the error, both inside the horizon and beyond. And here we show the robustness of our model with respect to the change of the grid. As you can see, the first case is very simple. You keep the same point during the train and during the test, we change only the grid. And the dyno will keep the same performance in horizon and beyond. However, our other question will fail. Also, in a very extreme case, here we use 100% of the points during training, and we use only 5% of the points for the test. As you can see, dyno will keep its good performance. However, the graph-based neural network cannot resist to this change. And on this slide, we show the capability of dyno that works on different geometries. On the left, you have Navier-Stokes equations on the plane, and on the right, you have the shallow water equation on a sphere. And both of them are evaluated on the 2 times grid, 2 times tensor grid than the training reference data. And then I'll play the video how it works. So as you can see, when time is green, we predict within the horizon. And when time is red, we will predict beyond the horizon. This video, I don't know if it's playing, it can play. Oh, sorry, I can play this video. As you can see, dyno performs pretty well, both on this rectangle plane phenomenon and also on the sphere. Okay. So in this presentation, I've shared with you our main contributions to of this thesis on first hybrid modeling, on some generalization problems, and also on continuous modeling. All these results have been published in different international conferences, and all these promising results encourage us to think about how can we push all this idea of using deep learning with some future directions. So I'll talk about some of these. First, current architectures handles not that well the change of boundary conditions. Sometimes you need to change the implementation itself of the architecture. So it's very interesting to see how can we make models that generalize to a lot of different boundary conditions. And also in many real-world problems, we have a lot of phenomena that take place in very different geometries, very irregular geometries. So it's very interesting to see if we can propose some models that can condition our prediction on a given geometry. And also in real world, we don't have the observation of the entire state of many systems. So it is still under discovered like this. It is still very interesting to add some physical information inside this kind of system to predict partially observed systems. And also, as you know, we have currently very high new operators, which is called pins. These architectures are conceptually very simple and maybe easy to make in place. However, when we try to use it in reality, it does not work that well. And this is due to some challenging optimization problem inside. And it is very to see if we can propose some alternatives already to this level. Thank you for listening.
Thank you very much for this presentation. Well, now it's question time. So I'm going to ask the first reviewer, so Christian, to start with this class.
Thank you very much. Thank you for this presentation. Very nice, very clear. First, I would like to thank the supervisors for this invitation to this really, really interesting PhD defense on the topic which I really like. I read your thesis with great interest. It is really nicely written. the contributions, but also the related work. And I will definitely give it to students who want to start in this area, which I don't do with every thesis. So this was really valuable. I wrote in my report lots of the things I appreciated. I will not go over that, but just a couple of things which I would like to mention before I ask questions. So first of all, the contributions are really strong, but what I particularly liked were the theoretical contributions. In control theory, there is lots of theoretical work, but not always linked to machine learning. So while people working, for example, in dynamical systems and control theory might have lots of work on the dynamical evolution of error, etc., but actually they don't always study the effect of data, because normally they don't do that. So it's a very recent phenomenon. So the fact that you actually used classical learning theory and applied it to dynamical systems, that's something which I really liked a lot. And the last thing I would like to mention, which I also wrote in my report, is the consistency. There are lots of different contributions in this thesis from various chapters, and it's not at all obvious to reuse this contribution in later theses. Very often, PhD students do something really nice, but it doesn't generalize to later work, so they throw it away when they attack other problems. And here we see really a thread going through the thesis, and lots of aspects are actually remain consistent. So I really appreciate that. So I'll ask a couple of questions, and I will not be able to ask all of them because you did so much work, so many chapters, meaning lots of questions. But I'll start perhaps with affinity. So affinity has this decomposition between the prior model, where you need to estimate the parameters, but basically you know the equations, and then the residual term. Do you have an idea what the effect is on the amounts of data? So if you increase the amount of data, I would imagine that one of these terms goes down, one of these goes up. Did you have the possibility to check that?
Yeah, in fact, it's very good question, and this is a problem that we did not discover in this paper. But what I want to say is that if we augment the amount of data, maybe we will have a very nice improvement in the machine learning model. It's, in terms of for example, for the physical model, I don't see any reason to improve its, for example, the precision of the estimation of the prompt. Maybe it will be more precise when we predict all these parameters, but more data won't do it will harm this prediction, but it won't help out also.
Okay. What about applying this kind of method on data which you have less certainty that it follows the equation you want? Sometimes you have data where you roughly think it should actually follow the differential equation, and one could argue that everything is a differential equation in life anyway. But you measure data, and do you think this kind of method would give improvements?
I think because when we propose this model, we mainly focus on not noisy environment first, and also this system is entirely observed. So if we try to apply on this kind of data, which you have some kind of, it's a partial observation, or it's a transform of this observation, you may need to add encoder or decoder, or some transformations to make sure that the data with which affinity work follows the differential equation.
Right.
But the model itself won't correct this. I don't think so, because
there is the risk that basically the prior model doesn't do anything. That's possible, right?
it is possible. It is possible because we propose to mainly for this kind of perfect data perfect data we don't have in any real world application. But we try to go towards this direction.
Okay. Actually, there was one question which I wanted to ask at the end, but since you mentioned noise, I will ask it now. So in all your experiments, you actually, most chapters, I think in all chapters, you actually studied the noise-free cases, right? And I'm wondering why this is. Is this for theoretical reasons or for practical reasons? Because practically you could simulate with noise, right? Why would you not add noise?
It's kind of the philosophy of the way we try to propose all these models, because we try to first we are not sure if our model works, even for the data with noise. So in this work, what we want to do here is to verify first if it works, and then if we have some further development, we can add some components to treat data with noise. Okay, it's just to in fact, this model is to prove that even to eliminate other to eliminate other factors that influence, for example, to influence the observation of our. I'm sorry. To influence that how. Sorry, I'll restart. Because when you add noise, sometimes when you add a neural network, it will absorb the noise of the data. Sometimes it will correct the noise. So we don't want that our model we don't want that our model learn at the same time the noise and the partial dynamics. So we want to make sure that our model will model this lacking part of the dynamics. And then if we can apply them to data, we have to consider other factors. Okay. Because I think in our team, in our laboratory, I have discussed with other PhD students. They have some application to noisy observation, noisy observed systems. And they told me that when they try to apply affinity on them, the machine learning term will correct already the noise.
That's what one would suspect.
This may fail.
Okay.
This may fail. So it may require a lot of further improvements.
But just one follow-up question. I mean, in general machine learning, you don't want to learn noise, right? Well, yeah, unless you have some bias term in your noise, then obviously you would like to pick it up. Mm-hmm. So this is a general problem, right? And then it should not actually impact the fact that you decompose into prior and into the data-driven term, and the prior term will not be impacted. It will be the data-driven term, and this basically means that you have almost a classical machine learning problem where you need to deal with learning, right? So what I'm saying is, I have the impression that you're not so much impacted by that. The fact that you do this decomposition. It seems to be a classical problem. You need to be capable of handling noise, right?
I think it may be capable to handle this case, but when it absorbs a lot of noises like that, I think it may be it will influence, for example, the performance of the model in terms of its estimate parameter.
Okay. Okay. Thank you. Let's go to the next chapter. I'll just ask perhaps a single question here. So you had a couple of theorems, one on the impact, most of them were expressed as the number of environments, and one was on the impact of the global term as environments increase. And I specifically was interested by the one where you have a given budget of samples, and for a given budget of samples, when you increase the environments, you get higher sample complexity, right?
Yeah.
So I was thinking about that, and I found that interesting. And so where does this information come from intuitively? I mean, you can kind of get at it when you look at the theorems, but is this because you have more labels on the environments? Where do you have more information in terms of labels? Is this alone where the increase of sample complexity comes from?
It's a very good question. And I will try to answer this. So, if I understand well, you could say that when we increase the number of environments, we will have larger capacity of this model, right?
If you have n samples, n being
N
whatever, 10,000, right? You might have a single environment with 10,000 samples, or you might have 10 environments with 1,000 samples, right? The global amount of samples is the same. And what your theorem says that if I increase the number of environments and the total number of samples stays equal, sample complexity increases. So it's better to have more and more and more and more of environments, which means in the limit case, you have 10,000 environments with one sample, right? So
I think it will help because when we try to share these common terms, this shared term itself, it will see many data when we increase the number of environments. If we keep we will increase the number of these the samples. So the complexity itself. Sorry. Sorry.
take your time.
I'm sorry. So when you increase the number of example and also the number of environment, when it's shared, when we have this common term, which is shared across all these environments, I think even if we have some increased complexity in each of these individual terms, however, the decrease in this common term will somehow surpass this advantages. I'm not sure.
Okay, I'm not completely sure about it. Doesn't it also depend on how similar they are, right?
Yeah. In fact, what we consider here is are some environments that are very similar. For example, we have the same system, but the changing thing is some background, for example, background context.
But even then, if you have a single environment, you have a full global model, and the residual will be zero, right?
So in this case, it depends on what kind of differences among these environments.
Okay. Because basically you have a trade-off where you say if you have more environments, then probably your global model gets more samples, right? But each individual term gets less samples, right?
What we stated there, I think, as you say that we have I think I see. I think I have a graph here to show you. It is not this graph. Also, I'm sorry, I don't have this graph to show this. However, when you have a total number of fixed total number of this environment, if we don't share them among all of them, yes, it won't share among all of them. It will increase the model complexity, and also it will influence the generalization. So in this case, our solution is to use them all, but when these environments are very different, we don't have solutions.
That makes sense.
Yeah.
This makes sense.
Mhm.
I think my question was a little different, but it's okay. It's okay. I'll continue with chapter 6. At some point, you say that all your environments have the same equation but different parameters.
Yeah.
Is this a choice driven by application? Because I don't see any requirements in your method which
Requirements
that?
on which
sorry, that's chapter 6, coder.
yeah. Requirements on the knowledge about the parameter or
Not the fact that it needs to be the same equation.
yeah.
I don't see why this is required by a method. So I think, do you confirm this is just a choice you did for experimental
choice.
reasons?
It's a choice.
It
It's a
could
choice.
work if this was not the case, right?
Yeah,
Yeah.
it's a choice because we, as you can see, we mentioned before, we try to model a family of model.
Yeah.
So we did this choice.
Okay. So another question on coder, and there is something which is similar to Dino, which in both you use the hypernetwork to predict the networks of another network.
Okay.
And so here I was quite interested in that because I shamelessly will cite work we have as well, which doesn't do that, but basically instead of writing or predicting network parameters, we're reading them. And so in our work, we found out that one of the issues you can have with that is that networks are reparameterization equivariant, right? If you have an MLP, for example, and you take units of this MLP and you permutate them, it's the same MLP, right? Because there is no order, but the weight matrices are different.
Mhm.
So that means if you take two consecutive weight matrices and in one you permutate lines, rows, and the other one columns, you will get the same mathematical function, but you do not get the same matrices, and you do predict weight matrices. So what's the impact of this on hypernetworks? I think this is not necessarily a question to your work, but actually to the work you use, right, to hypernetworks.
In fact, yes, it's quite interesting because we didn't see what's going on inside this linear hypernetwork. However, we generalize these networks because this hypernetwork it is linear. So each of the dimension is linked to this very small network. So there's no issue of permutation, I think, because we have identified each of the we have aligned all these dimensions.
I forgot about that. So the network for which you predict the weights is linear.
Yeah.
Then you don't have the problem. Okay. What would you do if it wasn't?
Didn't discover that.
Oh, no, that's okay.
Because what we thought about, for example, this linear hypernet. Why we use this? Because when we try to use when we try to learn a code like this, if we added many layers before this input, why can't we just remove all these layers before and we take just the last layer? Okay, so we just keep it, and we didn't think about using a nonlinear hypernet, but if we have some information that we try to inject into this network, for example, you have prior information about the system, you can do this. You can add nonlinear transformation and then inject the information. Okay. Yeah. Perhaps one last question to Dino, because I don't want to skip a chapter, and Dino is really interesting work. So I was wondering whether the modulation you do is a necessary step. It's really nicely done, but is it really necessary to predict the parameters of your INR? Couldn't this just have been a decoder which gives an additional entry input? Yeah. This is a very nice question because we have a lot of work that have already done this. before.
Yes.
For example, you just add some code beside the input, and then you can already condition well this the neural network. I don't. In fact, in Dino, we didn't see we see some differences, but we didn't discover this side. And in Coda, what we try to do is to compare if we just add this code at the input, if it's changed the result. And the answer is it depends. It depends on the type of the system that we consider. For example, if we consider some types of system that we have parameters, that is you have linear relation between the parameter and your term. It's a linear combination of.
If it's a very simple INR.
Yeah.
Only
So
then.
in this case, you can say that you put the condition on the input or anywhere, it won't change much. However, for some other systems, for example, we have a very large system. I don't remember which this. Sorry. So actually, sorry for this inconvenience. So as you can see, we took a system like this, this oscillator, this very bizarre oscillator. You have some parameters that is over the division and under the division. So in this case, we show that in experiments that when we try to modulate the last layer, it will work better than you just put it alongside the input.
Okay.
Yeah.
That's interesting.
So it depends.
Okay. Good. I'll stop here. Thank you very much. Back
Okay.
to you.
Thank you. So it is time to switch to the second reviewer, Alexandros. Can you hear us?
Yes.
Okay, you can go.
Thanks a lot. Thanks a lot for a very clear presentation, and I have to say that the manuscript also was very interesting, very well written, very good state of the art and situating the work that you did in the relevant context. So I really enjoyed reading that. So if I look at affinity, leads, and coda, they all kind of share this additive decomposition.
Yeah.
And already in the presentation today, you said that this is not really an issue, while I can kind of see why this is not an issue in for leads and coda, because you have a function, an unknown function that you want to learn, and actually you decompose it to two components. I'm wondering whether this is not somehow restrictive in the case of affinity, because you have a component, the prior model, and is this really general enough to cover all sorts of scenarios in which the data component might act as a composition of, not an additive composition of the dynamics component? So
Yeah, I understand. I think it's a very good question, because when we ask ourselves if this additive assumption is enough, or it is good. So for the physical model affinity, we have some issue. For example, when our model does not verify when the known physical model the combination of the non-physical model and the other parts of the dynamics does not correspond to this assumption. We will have trouble using it, but we propose this because it's very nice. It's a very nice decomposition, and we have a very nice property in theory, and we can find these parameters. However, if we can discover all the other assumptions, but I don't have to say that it is not restrictive. What we stated, that is it is not restrictive, but it is not the ideal solution to decompose all these dynamics.
Okay, so I mean, I'm not sure I got it. So you are saying that there are cases in which an additive assumption, at least when it comes to completing a known dynamical system, might not be enough or might not be appropriate.
Yeah, there exists some of these dynamics. Yeah.
Mm-hmm. Okay.
However, in most of the case, we suppose that this should work. Because in physics, I've mentioned before, you have some additive forcing, which is added at the end. So for us, it's not sufficiently general, but
it's good enough. Yeah. I mean, in the dynamical systems that you considered in the way that you were hiding the components, that was okay. I mean, because you were removing additive components. So I can say that in the experiments that you did, this is a valid assumption. I was just wondering whether this is not a bit too restrictive, and whether there are no other kind of dynamical systems in which we could have more complex interactions. Okay, given the additive assumption, a reasonable way to select a particular solution is doing the regularization as you did, the L2 regularizer. Otherwise, if you don't have a regularization, there will be an infinity of solutions on the theory components that will always be corrected by some kind of data-driven model and still explain very well, and maybe even predict the evolution of your dynamical system. But the regularization that you are doing commits you to a particular solution on the physics side. So the parameters that you find, if you want, on the theory side, depend on the type of regularization that you are doing. And
also, yeah, sorry, you go ahead.
Yeah, and also not just the regularization, but also the strength of the regularization.
Yeah, because in fact, we first try to solve this how to say that. At first, we proposed these methods with the proposed optimization problem. For example, you have affinity in which we minimize this norm. Yeah, and we have a central objective that is the minimization of this norm, and also for leads we have the same thing. So
yes.
In this way, if we, in fact, there's a lot of other factors that influence this result. The first one, what we used in affinity, if I remember, it was the norm, approximated norm. So if we use this kind of norm, actually we will have and if we operate directly with the function itself in a continuous way, we will lead to this parameter estimation result. However, if we try to implement it in practice, of course, you have some influence on the choice already of the estimation of this norm, because when we try to estimate it, we have only a set of data to estimate it. So if this changes, this will also influence the results of the prediction. So the results that we had in theory is in theory, and in practice we observe somehow correlated the results. But as you can see, we did not recover the exact parameter.
Yeah. So,
This may due to the fact that we use, for example, a limited amount of data, because when we don't observe the entire dynamics, so we cannot minimize the exact norm.
I'm wondering whether it is even possible to, or it even makes sense to be able to recover the exact values, because I mean you have these two terms, an imperfect physics model and a data-driven component. If I am making an error here, I might be correcting it with a data-driven component. So I mean, I'm not sure there is a guarantee on being able to recover the exact solutions, unless you for sure know that the regularizer that you are choosing makes sense also from a domain point, from the physics perspective, and it is what is driving you to the unique solution. Otherwise, I mean, why should I be able to recover the ground truth? I will recover something that, when combined with a learned network, will predict nicely, which is what is your objective. So where I want to go here is that I mean, I like the hybrid approach because it gives you a lot of interpretability, and we would like to be able to explain the results of the model. But I mean, there's a bit of danger here on the side of regularization, and the solutions that we might be getting on the theory parameters might be biased, if you want, by the regularizer that we are using. One could think also other regularizers, such as the output of the data-driven component should be uncorrelated with the physics component, instead of minimizing the effect of the data-driven component, or combinations of them.
I think it's a pretty good idea to decompose them, but in our framework, I think it's kind of difficult because all of these components are learned with data, and we cannot escape the effect of data and its estimation, the choice of this regularization. So
No. I mean, I'm not saying you can avoid that. I'm just saying that one needs to be careful. And in fact, my colleague Naoya Taikesi had some work on exactly that problem that appeared this spring on studying the effect of regularization in hybrid systems. So there's no answer unless you have a very strong domain knowledge that tells you what is the right regularizer. There is no really informed way of choosing such a.
And also, when you try to regularize the part of the data-driven part, it's always biased because you are always descending. You're always minimizing this term, so there's always some bias there.
Yeah. So I mean, I'll still stay a bit on affinity, even though it's your oldest work. So here you are bringing inside the learning model the differential equations, and you need to optimize parameters of this differential equation. So this is not always an easy task. It's a more difficult optimization problem compared to optimizing the parameters of a neural network. So what was your experience with that? And I mean,
My experience in this work or in general?
I mean, even better in general.
I think it's we did have some tricks on this because we in fact when we try to optimize this physical parameter, in the first place we choose some random parameter to initialize this parameter. However, it sometimes if we try to apply it directly, it's very difficult to optimize. This thing I can confirm. So in Affinity, what we did is to initialize this, not that far from we put on a restricted set of parameters so that it worked well. But if we try to address the problem of the optimization of physical model, because they were not designed for this. So we have to think about other problems.
So I mean, yeah, this is also something that we have observed. Do you have ideas of what might be better ways to optimize this hybrid thing, neural networks and physics-based model together?
So immediately I don't have answer because we did not try to distinguish these two parts, because in Affinity, as you see, we consider these two parts as equally. We did these parameters equally using the same algorithm and with the same way. So it is quite interesting to see if we can specialize the optimization for one part, because you have already very strong physical parameter inside. So if we can avoid some problem by using some other optimization algorithm for one part, and we keep the normal optimization for the data-driven part. So I'm sorry I don't have an exact answer, but
yeah. So moving a bit to the following chapters. So going to leads, you basically drop leads and coda. You kind of dropped the access to this analytical.
Analytical part. Yeah.
And you become completely data driven. And you in both chapters you have more or less the same assumption that you have multiply systems, and you decompose your parameters to a global set of parameters and a local environment specific set of parameters. In chapter 5, the generalization to a new environment just appears somehow as a small experiment, if I remember well, while in chapter 6 in Coda, it's the main focus, being able to move with very few samples to a new environment.
In fact, the insight here is still somehow under addressed, but I think we have some answer about, for example, when we try to adapt just locally, why we adapt well, because first we simplified already the optimization problem. As we seen before, we have a very smooth, very simple optimization problem. And also we, when we try to search only on a very local region around this data set, we have a smaller capacity of the entire model, as we have shown in these, in a different way, because we don't have proof. However, you can see that with a limited capacity of the entire model, we can generalize better. We can definitely analyze some generalization bound for this thing, but I don't think we have much of progress on this, if I remember well.
Yeah, so yeah, I mean, I'm just trying to see whether I got kind of correct the context and the difference between the two chapters. Basically, what you did in Leeds, you could have also, and in fact, you already evaluate that scenario in Leeds. You could have used it in the setting that you explore in Coda to fit this additional environment with very few samples.
Very few samples.
Yeah.
Sorry, you go ahead.
Yeah. So the difference between Leeds and Coda is how actually you fit or how you model these additional local parameters.
Yeah. In fact, in Leeds, we did not try to modulate a known neural network. In fact, we add a new term, which is another network. So what we basically did in Leeds is in terms of the function, which means that we have in the function space.
Yes, in one you operate in the function space, and the other you operate in the parameter space.
Yeah, but when we proposed the Coda, first, what we considered was not this idea. First, what we considered is the solution provided by Christian. It is just to concatenate a code just besides our input of the network. And then we say that sometimes it's not working, sometimes it's working. Can we generate this idea further? And then we found this idea, which is quite similar to Leeds, but it works in parameter space. As you can see, we don't have any theoretical result inside the Coda because it's like we have some. Sorry. Yeah.
Sorry to interrupt. Let me just get it straight because I think I missed this question before. So one approach would have been to attack the type of problem that you attack in chapter 6, just to add an additional set of parameters as input to your neural network, which will be tuned specifically for its environment.
Yeah.
Okay.
I'm sorry. Can you repeat the last sentence?
I'm saying you could have taken, as you said, the Leeds architecture, extend the input values with a number of parameters that you would use to model the specificity of its environment. So you would extend the representation of your instances with a set of parameters that would be now parameter
of the system. Yeah. In fact, at the beginning of this project, we didn't consider this kind of higher information, for example, physical parameter. So we started with this idea of generalizing towards multiple environments, and we have to propose. We propose this idea, and then we have some very interesting and very surprising discovery. We can see that, as you can see here, sorry, this space, this red grid, as you can see, it's very regular. It's in fact, we trace this surface in the same order of the parameter space, in the exact physical parameter space. So we discover this by accident, like that. It's kind of excellent. And so we try to understand what's going on behind this, why we have this kind of bijective behavior between the real parameter and this random code. So we add some part to try to explain what's going on behind, but we didn't start from this.
Yeah. So what we see in the grid is the Xi parameters on Coda.
Yeah, because you can see that this is the first dimension of Xi, and this is the second dimension of Xi, and we trace them with the grade of parameter, the exact system parameter.
Okay.
So you can see that this have a very nice structure, and this allows us to extrapolate to well around it. And I don't, to be honest, I don't know why this happened. Why this is happening.
So are you saying that there's a kind of physics interpretation on this space?
Kind of, because what we discovered, as we shown in our later analysis, we did some theoretical analysis to try to understand what's going on. So basically, when we try to do some auto decoding, we try to send information to this code, to this very compact code, and then if our function lives in the same space as this code, for example, our function varies with 2 parameters, so it lives in a very low dimensional space. So when we try to encode this function through the data, through the gradient descent into this code, maybe it will recover the same thing inside the parameter space.
Yeah.
So we do some kind of translation between the data and its parameter automatically.
Yeah. That's a nice intuition. So you are saying that Xi is much closer as a space to the physics parameter space.
It's closer to a what I didn't remember was stated. It is closer. I'm sorry. You reference to the phrase on.
No. I mean, I'm just restating or explaining my understanding of what you said. By projecting in such a lower dimensional space, you are kind of much closer to the parameterization that we have in the physics model.
Yeah, it's not the exact parameterization.
Yes.
It's kind of we have the same structure, we have the same order. Also, we have the same order inside. So it's sometimes you can flip this surface around. You can do some translation. You can do you can do any other things. But if we apply our minimization, we will find this very nice not rectangle. It's a very nice square like that.
Okay. A last one, and I'll stop. Why you kind of gave up on the hybrid approach and you focused only on data-driven in the follow-up?
Okay, this is a very good question, because in the first place, we started. In fact, I started my thesis with a bunch of PhD students already in 2017, and we have we tried to consider some particular parts, for example, for in the project of leads, to extend this idea of hybrid modeling, because as you can see, as you stated before, we can use maybe a lot of environment, and we can maybe improve the optimization of the physical part. But we didn't see if it's very interesting for our community, so we try to say, okay, let's focus on only data-driven basis, driven models, because this is still some new questions inside this domain. So we focused on this, and we kind of not abandoned, but we leave it aside. Yeah.
Okay, thanks a lot.
You're welcome.
Okay, thank you very much. So we move now to the other members of the committee, and I would ask Professor Gustavo Camsan. Can you hear us?
Yes, can you hear me?
Yes, perfectly. You can go on with
Okay.
questions.
Perfect. Well, first of all, congratulations, Yuan, and to you and your advisor. I think that this is a fantastic piece of work. I have like a lot of notes in your thesis. It was really a pleasure to read it. And actually, I mean, you read 4 fantastic papers already. So I don't have too much to say. I mean, in the end, this is a thesis that it has been already evaluated, and yeah, I have nothing but compliments to your thesis and your advisor, and everything's really fantastic. Also because I love the topic and you know, bridging these 2 fields of deep learning and dynamic modeling, it is really timely. And I have a bunch of basically of curiosities and also like general questions. We used to ask a lot of general questions in Spain in thesis defenses, right? So just to check how close you are to be a doctor, right? In the old kind of Spain, right? So let's try to have this kind of more scientific high level discussion about what a hybrid model means and other concepts that we will pop up probably in our discussion. So maybe before going to the general questions, maybe I can just shoot very specific questions, one per methodology that you have been developing. So because basically I have like a lot of curiosities and also like some punctualization. So the way you selected at some point doing one thing in one way or another. For example, I don't know, let's start from the beginning with the affinity model. That's actually a very nice model. Actually, we started in the lab in a very similar fashion, in a very similar way some years ago. We stumbled on the concept of identifiability and equifinality, right? In the geosciences, we use equifinality, right? Or what people in causality call being right for the wrong reasons, no? So you can actually identify parameters, which apparently they are kind of okay. Actually, Alexandros already put that issue, right? So you're basically combining two kind of functions. So maybe one is right and the other one is like diminished, but in the end, maybe the parameters that you identify are both wrong, or the other way around. They are right, but for the wrong reasons, right? So I would like to hear you about these things. How can you really control, if you can, and also I think another issue, a related issue that appeared in the conversation before, it was about the experiments, right? That you put in here, where most of them there were noise-free setups, and I think that noise plays a crucial role here. I mean, we are talking about prior knowledge and regularization, right? So I would like to hear your opinion about that. I mean, about these issues of identifiability and how can you control about that, right?
Okay. So for the first question about identifiability, in fact, in our affinity framework, we have supposed that we have only, or in fact, we proceeded like this. We suppose that we have a single solution, and then we try to identify it. So we have this physical model that includes one and only one solution to this one. So when it becomes harder, for example, when you have a very, because what we considered was parameters in very low dimensional space, because we have 2 or 3 parameters inside. And when we have a very large number of parameters, even if you have the identifiability, with the optimization we have here, may won't work at all. So there's 2 questions. There's already 2 parts of the issue. One, if it's identifiable, if it has 2 models already. In this case, can we choose it? I don't have answer because when we try to learn from data, we don't want it to prefer one to another. If we have some bias, for example, if we have some bias that we want to inject into, for example, we want the parameter that is close to something or resemble to something that is more reasonable, we can do this. We can add some bias. But if we just learn this blindly with only data, I don't think we can solve this problem properly.
Yeah, actually, that was the thing that struck me the most, right? Because typically in domain sciences, you know something about the system that generated the observation, right? So you should, I don't know, you should kind of put more effort in designing the regularizer somehow and trying to force other than the energy that you're putting there, right? So designing is like I don't know, simplicity, right? So maybe you want to impose some sparsity, or maybe you want to enforce some kind of dependency with something else, with ancillary variables, ancillary processes, something like that. No, I don't know. I mean, it's nice because you have like a beautiful framework, but in my opinion, it's a bit underexploited, right? So don't take it like a criticism, but it is something like, oh shit, I wanted to use this for something else because I know something about the problem, right? So I was actually expecting like, scrapping a little bit more on the domain sciences. So, you have a framework, so you design the proper regularizer to tackle that particular problem, right? I don't know if maybe you already explored these sort of venues. I don't know.
In fact, I think we are trying to do this, but because in our team we don't have that much people, so we try to discover different directions. Sometimes the energy is limited, and sometimes I think Patrick can confirm we have some collaboration with other teams inside the laboratory. We try to extend this idea further on real data, on noisy data, or on partial observed things. We tried this, but from now we have a lot of difficulties. I think we need some time to digest it, and but it's quite interesting to see if it can be extended to this data.
Great. Thanks for the answer. Maybe let me just jump to the leads and this learning from multiple environments. I struggle a bit with this chapter actually, especially because I did not get quite well, I think, these conditions for uniqueness of the solutions. I don't know if they are very, very restrictive in the end, So, I mean, in real scenarios for sure, but even in the experiments that you run, I don't know okay, I don't know. Can you please clarify a bit this? How restrictive is the assumption for getting like the unique solution in that case?
And the assumption about the function R.
Yes.
Yeah. In fact, it's quite. It's not that. However, the restriction on this R is not that strict, because what we stated, if I remember, this is a very old paper. If I remember, we say that if this function is strictly convex, then we have a single solution. However, the objective here is to have a stable and unique solution at the end.
Yeah.
The common term, if we can recover some system in this common term, no problem. But what we want at the end is only a stable guarantee for this.
And I guess that you put the same kind of constraint on the R. It was R, right?
It was R. Yeah.
Yes. Yeah. So sometimes, well, quite often actually, you have misspecified models, right? For different environments. I don't know how the framework
for different models also. Yeah.
Yeah. So how can it work in I don't know, in the regime that you don't have enough samples or misspecified model for that case?
You mean in the region of data?
Yes,
where
for example, or that you do not really have like an intuition about the model complexity or you know.
Yeah, in fact, when we proposed this, we have looked at the current work on the complexity of the model that we try to use. For example, we demonstrated it with first a linear model, a linear operator, and we found a bound for it, and we found a value that corresponds to the capacity of it. And for the neural networks, we have also this in fact, for the neural networks, it's quite harder because we don't have we have some theory, but there are many bounds that are way too large to what we observe in the real world. So, however, we tried some quantities or some things inside this theory, and it worked. We know it will lower the bound, but lower the bound is not enough. However, we can see that in reality, it indeed improved the generalization error. So if we want to use a new model, for example, a new model other than your network or other, I don't know, a new type of neural network and your operator, etc. We need to find out also these quantities. We have to identify all these quantities that allows us to show how complex this model is.
Yep. Nice. Yes, thanks. Let me just jump now to the CODA sort of environment. It was very inspirational. Now we are working not that much in this hybrid modeling, but more in another related field, which is this equation discovery and symbolic regression. So in the end, you want to learn an equation that expresses, I mean, from data, right? From observational data, or an equation or a law. And here we are often talking about a triad, right? So you want that the model should perform well. You want a model at the same time, it should be most of the times well regularized, typically simple, right? Simple expressions, simple laws are most preferred. But also at the same time, you want a model that it is certain, or at least it reduces uncertainty in the in-sample regime, and basically, yeah, you cannot actually extrapolate very well in the out-of-sample regime, right? So, and then that triggered my question here, because I mean, it's really fantastic work what you did with deep learning, but you're kind of missing a leg, an important leg, which is uncertainty quantification in both parameter space and also the prediction, right? So, I mean, some years ago, I became partially Bayesian, so I would like to learn a bit more if you have been playing around with uncertainty estimates or quantification, because in the end, you want to learn parameters, but not only parameters, but you want to be certain about the identification of the parameters, right? And I would like to know a bit more about your experiences, if any, on that.
Yeah, this comes to the end of the work, because at the beginning we didn't know we have such model that discovers parameters, and at the end we say, okay, let's use it to estimate parameter. It worked. We're very happy, and then we say, okay, is it well this parameter? Indeed, we have. I'm sorry. I think I have a slide on this. Okay. This one, and this one. In fact, we traced, we have mapped all these estimation of parameter. So as you can see, when we predict well inside this complex code, we have not that much error. and outside around we don't have that much error. However, when the loss itself, the loss of adaptation is very high, for example, here you have some loss of over 20% or 30%, even higher loss. You are not that good in parameter estimation.
Sorry to interrupt, but this is not uncertainty, right? This is just error.
No, this is the error. What I want to address is that maybe in terms of already this is an indication, right? You can say that if it predicts not that well, we can't trust this estimation here. We can see, we can already see that we can already try to reference to this error adaptation to see to let it be an indicator of this. However, but in fact we have no uncertainty inside this inside this process, because what we do literally is to transfer the information of the data to the code. So
yeah, but what I mean is that it would be really nice to have uncertainty estimates in that end. So even if you're committing, like, I don't know, a lot of error in the edges, maybe if the model is uncertain about that, you can tolerate this thing, and then you can even mask this out, right?
Yeah, I think, but
it is just a suggestion, right? So trying to look at the uncertainty estimates and eventually propagation on the parameter space. But yeah.
But in fact, we didn't try to discover this, because already in our domain of machine learning, we didn't see that much work on parameter estimation. So I think it's very interesting.
Yeah, I mean, it would be as simple as either putting a Gaussian process at the end of the output of your model, or GP on parameters, or I don't know, just take your big beast and apply MC dropout or MC or something like that.
I think it's,
yeah, I mean, there are different ways for doing that, right?
Yeah, because I think what you're saying is that we can use already something that exists to this, but we here what we well, it's not easy to state in the framework of the framework that we proposed. But I think there's something to do with another branch of studies that explicitly try to identify these terms and the parameters in front of them. For example, when we have Steve Brunton, who tried to this work, and I'm not because there's a long time I didn't look at his work, but I think maybe there is somebody who's trying to do this kind of modulation of the parameter, or who try to how to say try to I'm sorry, try to see if the results or the prediction given by its identified system corresponds to the real data. So in this way, I'm not sure about the answer, because we didn't work really on that, but I think it's still very interesting to see that come.
Sure. It was just a suggestion. I mean, don't take this thing personally. I mean, it's like, yeah,
no.
I just having a talk on that. Okay, so yeah, there were, I had like a lot of questions more, but since most of them they were already asked and answered, so that's the advantage of being the last one, or almost the last one. I have, even though I have like a couple of general questions that we used to ask to every single PhD student in Spain. So yeah, maybe I will go for one of those, right? The standard question that we ask is always something like, Would you? I mean, if you started the thesis tomorrow, what would you do differently?
Oh, this question is okay. I stay. I don't know, because with the experiences, we accumulate a lot of experience during this thesis. So it's kind of different to say, and we have this the period is different, because at the beginning of my thesis, it was before the COVID. Okay, this was the last decade. So and also this domain itself is changing fast, because we don't have the main the exact same focus right now as 3 years or 4 years ago. So if I start today, maybe I was already I've been already starting to study my last model, maybe, but because it is trendy and it is very popular inside the domain, and I will begin with this, and then if I discover other things interesting, I will start in other directions. Yeah. So begin with something that works and that helps you to understand what's going on inside the research, and little by little you can develop to confidence. Yeah, good time.
Thanks, Yuan. Actually, this brings me to the second general question, which is something like, from out of the 4 models that you developed, which is the best and the worst? It's a tricky question.
Sorry, can you repeat the question?
Out of the 4, let's say, main developments that you did, which is the best and your worst, or the preferred and the less preferred? You have to think carefully.
It's quite, yeah, I think it's very interesting, because among all these 4 models, for the first one, I began with collaboration with some very senior PhD students, and they have lived. And I started with it, and I tried to develop my first order paper. And then I put a lot of energy inside this third model, CODA. We spent almost 1 year inside it. I think it's quite interesting inside. We have still a lot of things that we don't understand. We try to explain it. We spend a lot of energy to clarify what's going on, to simplify the idea, to clarify all the other things. And the first one, it's I don't know, because it's popular right now, and we see some opportunity here to propose a method like this. So we did this in no time. And so personally, I prefer my third work, because I made a lot of efforts and with my co-authors, because without them, I won't have this result. Yeah, I think for example, the richest experience that I had is with the third paper. Yeah.
Okay, thanks for your honest answer. Yeah, I have nothing more to say and to ask. Thanks again for the presentation, the thesis, and your answers. Everything was really cool to hear and to read. Yes, thanks.
So thank you very much. So we move now to Samantha. Please try to stay.
Yes, I will be brief. Thank you. Yes. So I will join all my colleagues in saying that I also had a lot of pleasure reading your PhD, and I would add that this is all pretty far from my domain. So the fact that I could follow along most of your whole introduction and getting into the topics, and even like more than to the details, was a really good thing for me. I was really happy. It was very easy to follow and pedagogical. So thanks for that. I'm of course very interested in. I have a user perspective on what you're developing. You know, I'm using physical solvers every day, so every time I was reading one of your chapters, I was wondering, how can I use this? And so I'll just have a few questions as a physicist trying to use what you're developing, even if I mean, I think enough questions have been asked on the other aspects. The first one is, when I hear hybrid model as a physicist, usually for physicists, it kind of comes with a number of assumptions in terms of guarantees. For example, physicists really like it when you respect conservation laws from this universe, like energy or mass, and they get very, very mad anytime you diverge just a little bit from that. And a lot of hybrid approaches focus on you know, taking a physics equation and then targeting some of the terms in ways that are entirely constrained so that you can respect these constraints. I'm not sure, is that what's happening even with affinity? Because you're adding a direct corrective term to your physical fields and you don't really have a pure constraint on that, right?
Yeah, that's exactly the same problem because what we propose does not target this question about the regularity of the results, because when you go back to the introduction here, we have a very large number of hybrid models. So what we do here is that, but I think it is quite interesting to see if we can combine already this root idea with other techniques such like this. For example, we try to add some regularity on the neural network because we have in our domain a lot of invariant neural network. So if we try to apply that inside our model, we may add some nice properties to the hybrid model, and also we can add some constraints on it. But I think this term is this direction is still to be explored.
Okay. Yeah, I really like this, by the way, the description that you were trying to say that there are many things behind the word hybrid, because of course it doesn't mean much. So so it's interesting that you try to map out the different approaches to this idea. Okay, yeah, thanks. But then another one in the kind of same vein, I guess, but this is getting more philosophical, is you are, well, philosophical, but also practical. When you say you want to target corrections for physics approaches that are insufficient, if the systems are too complex, and so you're learning a correction for complex physics. But a lot of the complex physics that we pay a lot of compute hours to solve for are nonlinear and possibly chaotic. Because from my understanding, you base a lot of your loss functions on following trajectories. At some point, I'm wondering if you might not run into a wall, because two correct solvers, as in two very high fidelity physics solvers, starting from the same point, will agree for a time and then won't anymore. Yeah. So at some point, basing yourself on the distance to a trajectory and saying that if you're far, it's wrong, is actually no longer true. And this depends on the physical system. So have you thought about this? What are your thoughts about that?
I think my thought is like, because we have already this kind of question about who generated data, and then we learn from which kind of solution. It's like this kind of egg and who lays the egg, this kind of problem. So my think about it is that our already all these data-driven models based on data will have this exactly same. They will try to repeat they'll try to repeat the thing that they see in the data. So the quality you get in the data will influence its performance. Also, in terms of stability, it's also concerns the data. So in this to see in this way, I don't see any how to say that. I don't see much way out to solve this kind of problem, because already when you know exactly what's exactly going on inside a physical model, you can control this kind of chaotic issue. And here we want to solve. We can't solve the same problem that we have in measurement. For the moment, I don't know if we have already somebody inside this company, which have some ongoing methods. But I don't think we can.
Well, I can give you one direction, and again wonder. I don't see how that fits in off the top of my head with your approach, but the way physicists will validate a model is that they say it's okay. I'm specifically thinking about simulation of turbulent fields and things like that, where you're immediately into full chaos. Is they say, let's give up on just having the correct fields, except that they're meteorologists, because then they want to know where the actual vortex is. But otherwise, they say it's impossible to get the exact field. What I want is to get the correct statistics of the actual system. This is feasible in a physical setup. Here, do you think there is a way that you could include more statistical constraints into your model, into your training, in the sense that you would have a target to having a certain statistical behavior instead of a target that says you have to get every time step correct for a given period of time?
Yeah, I think this is connected to some work that exists, but I didn't try that yet, because we have inside our community, inside the machine learning community, large way, someone tried to model this kind of statistics with some kind of Bayesian neural networks. And also we have some works worked on this kind of Bayesian neural ODEs to add this function inside the solver. So maybe this will give some solutions to it, but I'm not sure about it. Maybe I have some. Well, maybe there are some other approaches that I didn't see, but this is one of the solutions.
Okay. Maybe in the interest of time, I'll stop here. Yeah. Okay. Well, then maybe I'll just finish up on a very I don't know. I have a practical question and a general one. But let's say the more general one is, you haven't talked here about cost. I mean, it's generally accepted, the idea that, solving for physics is expensive, and that usually machine learning enables acceleration. Probably, I would understand that maybe at this point you're not ready to offer an alternative to a commercial CFD software that's cheaper. But how do you think? Yeah, but I mean, how do you think that here you're putting a lot of effort into quality of your production, of the results you're producing, and showing that you're getting very close to PDE results. So usually the rationale with machine learning is, oh, I can give you, an approximator of physics. It's good. It's not going to be as good, but it's going to be much cheaper. Do you think here there's hope for actually reaching a point where you can get the same kind of quality as physical solvers, but still significantly cheaper?
It depends on what you want, because we have the cost to retrieve this data, because when we solve these equations, it's very, very, very costly. So if we include this, I'm not that sure, because considering the irregularity inside these networks, maybe it won't generalize very well. Besides, if we can consider all this lineup of hybrid modeling, it may reduce some irregularity in some of these results. But overall, I have some doubts also. Yeah, but some states that if you use this, like the paper I cited there, this Koshkov paper, which is produced by DeepMind, I think, they say that we can use a very cheap numerical model AI, and then we use the generality of the results given by a neural network to get the same quality of as the higher solution model. this state, I have a lot of doubts because I don't know why this works. Because when you try to when you try to correct this, maybe I did some errors, but it's okay. When you do this thing, for example, you have low quality methods, and you try to do some super resolution to these results, it will improve because you don't have single solutions. You have a lot of solutions to solve, and what you learn here with the data-driven model is the bias. It's a bias inside your data, and if your data change, if your environment change, or your scale change, maybe it won't work. So I have a lot of doubts, but we hope that we can one day inject exact physical information inside the neural network, and the neural network itself know how to use it, in a perfect way, but in a correct way.
Okay. Okay. Well, thank you very much.
Okay, before giving last words to the supervisors, I would also like to congratulate you about your nice work, and maybe two very short questions on my side. The first one joins a little bit what is said by Gustavo about the Bayesian approach. You know that I'm also quite fond of Bayesian approaches. And I was wondering if Bayesian formulation, even if you don't solve it really in the Bayesian way, but you simply solve an optimization problem where the loss function is formulated by using the Bayesian approach, could not be a natural way of incorporating in the model the constraints, the different constraints that you apply a little bit by hand with these parameters, which must be chosen by grid search or whatever. And well, you could maybe include them more naturally by using a Bayesian formulation. And I don't know what are your thoughts on this?
So what you mean is that we try to add some additional objectives, which is formulated in a Bayesian way, and then we try to influence the results that.
Yes, or maybe you can formulate things in terms of prior models and posterior models that you try to update, or you know, or model uncertainties. And also the hyperparameters you have in your loss functions could be formulated as you know, as prior assumptions.
Okay.
I'm not sure if it's possible to do it, but
I don't see right now what's the exact solution to this, because I didn't work on it. So,
okay.
yeah, and what I can say about it is that combining this equation, combining this equation method with a deep learning, it's still underaddressed. I think it's underaddressed. Still underaddressed because you have very nice model with traditional machine learning, but with deep learning, we didn't discover that much yet. Even if it's the same intuition, even it's the same way to work with data-driven model. However, you have some very unpredictable behavior inside the learning network. So I'm not really sure. Yeah, I think it's doable, but we have to deal with many other problems, many very special problems we see.
And maybe another one. Yes, it was about your hypermodel, because if I understand well, you have this hypermodel which learns how to correct the parameters which you have that you have learned initially on the common environment, let's say. And I was wondering how this approach compares to approaches where you learn smaller models and then you combine them by using gating functions. That's also kind of a hypermodal, right?
It's like we train a set of like basis models, and
Exactly.
then we try to
And then you try to decide in which part of the probability space you are going to apply expert one or expert two or expert three. This is
Yeah.
called, I think, this is called the mixture of experts.
I think it's doable. It's doable, and right now I don't think we are considering it. But as you can see, if we consider already our native code, we can already consider it as a kind of, how to say that, kind of a combination of some experts at the end, which means that if you remove the last layer of the network, you have already a basis, and then when we try to modulate this last layer, we will just limit this modulation to the last layer. When we do only the modulation to this last layer, we can say that we are combining some bases already. So it's doable, and I'm not sure it's very economic in this, and I'm not sure it's very easy to make it work. Because, because you have to already first learn the basis and then combine them. So you have two problems to solve at the same time. When you have not that good basis, when you combine them, you won't get a good result, and on the other way, it's the same thing. So.
Okay, so thank you for this. For these answers, and well, now I think that yes, we can move to Nicolas, maybe. Which order you want to speak?
Because I think all have to say that Yuan is something that you can expect from a PhD student and maybe more. Your work was fantastic. The discussion that we had was very, very interesting each time, and I liked the intuition that you have of the thing and the way that you explain this your intuition. That's very good. And your sociability was very nice, because before you arrived in the team, there was a small group of students that we initiate to this domain, to this field, or this environment. So, and you plug inside. It's very easy, and you take the role of the lead after some times, and that's very natural and very impressive to see the integration and the discussion and the dynamic that you put inside this field, inside it. It's very great. I think that Patrick also is very happy. This the 3-4 last years that we had today. So Patrick has supervised you more than me.
Okay.
You can finish.
Okay, so I will make a few remarks too. And so when you started your PhD, we were more or less at the beginning of this exploration of this topic. Well, for truth, we started 2 years before. We started slowly, and well, my feeling is that we made a long way towards our objective of exploration, so physics plus machine learning. And as Nicolas mentioned, this was a collective effort. I mean, we have been working with different researchers and different fellow PhDs. Okay. But well, we're really an important element in this collaboration. I mean, very soon you took the lead of different research directions. You proposed your own ideas, and you managed to develop them. Okay, well, so I think it's great work, and for me it was a pleasure working with you. Then I want to highlight that this was a particular period because of the COVID and the lockdown. Okay, so this is true for everybody who did a PhD during this period. But for you, it was probably more difficult. I mean, on the personal side, it was wow, it was more or less impossible to go back and visit your family in China because of the different measures. That's my far too complicated. Okay, and also on the it's a professional viewpoint, also because of the COVID, and there were a lot of restrictions on the visas. Okay, and for people from different countries, it was quite difficult to get a visa, for example, for students. So it was difficult for you to go and participate to the conferences or legislation. So I would like to really to congratulate you for your work and for your behavior, and also to congratulate you for your resilience. Thank you. That's it for me.
Okay, thank you very much. So we are done with the defense. So now we have to, I don't know, go somewhere to deliberate, or maybe stay here. And the public goes outside, I don't know.
Maybe we'll try to find a room and not maybe to reservation that and Alexandre and Gusto, I sent you a Zoom link. Okay, so we just maybe 5 minutes time for us to find a room, and then we connect on this one. Okay.
Okay. So I just je vais garder juste.
Restez là.
Oui, mais c'était YouTube, oui, mais c'était
Ouais,